AI Loss Functions Deep Dive: How Senior Engineers Master the Mathematics of Learning in Modern AI Systems. Episode 70. Welcome to Agentic AI World. I'm your host, and today we're going deep on loss functions, one of the most fundamental concepts every senior AI engineer must master cold. If you're interviewing at Google, Meta, OpenAI, or any serious AI shop, understanding loss functions isn't optional. It's table stakes. And yet most candidates fumble it because they treat loss functions as black boxes. Today, we fix that. Section 1. What is a loss function, and why does it matter? At its core, a loss function is a mathematical signal that tells your model how wrong it is. It takes the model's predictions and the actual ground truth, and returns a single scalar, the loss. The training process then uses this signal, via gradients, to update the model's parameters and make it less wrong. Think of it like a GPS rerouting you when you take a wrong turn. The loss function is the GPS signal. Backpropagation is the rerouting. Gradient descent is you actually steering. The choice of loss function is not arbitrary. It defines what your model optimizes for. Get it wrong, and your model learns the wrong thing. Even if the architecture is perfect and the data is clean, senior engineers don't just accept default loss functions. They ask, what does my model need to be penalized for? What errors matter most? What distribution am I modeling? Section 2. The core loss functions you must know. Let's run through the essential loss functions, what they do, and when to use them. Mean squared error, MSE. This is the classic regression loss. You take the difference between prediction and ground truth, square it, and average across the batch. Squaring does two things. It makes errors positive, and it penalizes large errors disproportionately. If your prediction is off by 10, your loss is 100. If it's off by 1, your loss is 1. Use MSE when errors should be penalized quadratically, like predicting house prices or stock returns where large misses are much worse than small ones. Avoid it when your data has outliers, because MSE will obsess over those outliers and warp the whole model. Mean absolute error, MA. Instead of squaring, you take the absolute value. ME is robust to outliers because a miss of 10 costs 10, not 100. But it has a problem. The gradient at 0 is undefined. In practice, this is handled, but it's why MSE is more common when data is clean. Huber loss. This is the best of both worlds. MSE for small errors, ME for large ones. You set a threshold delta, and below that threshold you use quadratic loss. Above it you use linear loss. Huber loss is the default choice for production regression systems where you want gradient stability and outlier robustness. Binary cross-entropy, also called log loss. This is your go-to for binary classification, spam or not spam, fraud or not fraud, click or no click. It takes the model's predicted probability and penalizes it based on how wrong that probability is in log space. A model that says 99% confidence for the wrong class gets hammered. A model that says 51% for the right class gets a gentler penalty. The key insight: cross-entropy lives in information theory. Minimizing it is equivalent to maximizing the likelihood of the correct labels under your model's predicted distribution. When an interviewer asks, why cross-entropy for classification? That's your answer. Categorical cross-entropy. Same idea, extended to multi-class. You have a softmax output that gives a probability distribution over k classes. Cross-entropy measures how different that distribution is from the one-hot ground truth. The gradient is clean and strong, which is why it's the default for classification everywhere. Sparse categorical cross-entropy. Functionally identical to categorical cross-entropy, but takes integer class labels instead of one-hot vectors. Saves memory and computation when you have thousands of classes. KL divergence, Kullback-Leibler divergence. This measures how one probability distribution differs from a reference distribution. It's not symmetric. KL of P from Q is not the same as KL of Q from P, which is an important nuance. In VEs, variational autoencoders, KL divergence is the regularization term that keeps the latent space smooth and continuous. In knowledge distillation, you use KL divergence to make the student model's output distribution match the teacher's. Contrastive loss and triplet loss. These are used in metric learning, when you want to learn an embedding space where similar things cluster together and dissimilar things are pushed apart. Triplet loss takes an anchor, a positive example, same class, and a negative example, different class, and minimizes the distance between anchor and positive while maximizing the distance between anchor and negative by a margin. This is the foundation of face recognition systems, recommendation embeddings, and semantic search. Focal loss. This is a modification of cross-entropy invented specifically for object detection in the RetinaNet paper. The problem it solves: class imbalance. In object detection, the vast majority of anchor boxes contain background, easy negatives. Standard cross-entropy wastes most of its gradient on these easy examples. Focal loss downweights easy examples by multiplying the cross-entropy by a factor that shrinks toward zero when the model is already confident. Hard examples get full gradient. This dramatically improves performance on imbalanced datasets. If you're interviewing for a computer vision role and you don't know focal loss, you're leaving points on the table. Section 3. Loss functions in modern LLM training. Now let's talk about how loss functions work in the large language model context, because this is where most senior AI interviews are going today. Pre-training uses next token prediction loss, also called causal language modeling loss. For each token in the sequence, the model predicts the next token, and you apply cross-entropy between the predicted distribution and the actual next token. This is averaged across all tokens and all sequences in the batch. The elegance here is that the loss function creates a self-supervised signal from raw text. No labels needed. Every token is simultaneously an input and a target. But here's what senior engineers know: the choice of which tokens to include in the loss matters enormously. In instruction fine-tuning, you typically mask out the prompt tokens and only compute loss on the response tokens. This teaches the model to generate good completions, not to memorize prompts. RLHF, reinforcement learning from human feedback, introduces a reward model and a KL penalty. The policy is trained to maximize reward while not drifting too far from the base model, measured by KL divergence. The combined objective is maximize reward minus beta times KL divergence from the reference policy. That beta is critical. Too low, and the model hacks the reward function. Too high, and it can improve. Direct preference optimization, DPO, sidesteps the reward model entirely. It directly optimizes a loss function that compares the model's log probabilities on preferred versus rejected completions, with a reference policy as anchor. DPO has become the dominant fine-tuning approach because it's simpler, more stable, and achieves comparable results to RLHF. Section 4. Common interview questions. Let me give you 5 questions you're likely to face, with the framing you need. Question 1. Why do we use cross-entropy for classification instead of MSE? Answer. MSE treats outputs as continuous scalars. For classification, we need to model probability distributions. Cross-entropy properly penalizes wrong probability assignments in log space, has clean gradients, and is equivalent to maximum likelihood estimation under the categorical distribution. MSE on probabilities produces weak gradients when predictions are near 0 or 1. Question 2. What's the difference between KL divergence and cross-entropy? Answer. Cross-entropy of Q from P equals the entropy of P plus the KL divergence of Q from P. When P is fixed ground truth, minimizing cross-entropy is equivalent to minimizing KL divergence. They differ when both distributions are variable, as in VAEs, where you minimize both reconstruction loss, cross-entropy, and regularization, KL. Question 3. How would you handle extreme class imbalance in your loss function? Answer. 3 options. First, use class-weighted cross-entropy. Assign higher weight to minority class samples. Second, use focal loss if you're in detection-style tasks. Third, combine both, weighted focal loss. At data level, oversample minority or undersample majority. At architecture level, consider SMOTE for tabular or augmentation for images. Question 4. You're fine-tuning an LLM. How do you set up your loss function? Answer. Standard cross-entropy on response tokens only. Masked prompt tokens. Use label smoothing to prevent overconfidence, typically 0.1. If doing preference alignment, DPO loss on chosen versus rejected pairs with a KL coefficient tuned to prevent reward hacking. Monitor perplexity on a held-out set as the real-world proxy for loss quality. Question 5. What is label smoothing and why does it help? Answer. Label smoothing replaces the hard one-hot target with a softened version. Instead of 1.0 for the correct class, you use 1 minus epsilon and distribute epsilon across all classes. This prevents the model from becoming overconfident, improves calibration, and acts as regularization. Standard value is 0.1. It was introduced in the original Transformer paper and is now ubiquitous. Section 5. Production gotchas. A few things that bite senior engineers in production. First, loss scale matters for mixed precision training. When using float 16 or float 16, gradients can underflow to 0 for small loss values. Loss scaling, multiplying the loss by a large constant before backprop, then dividing gradients, prevents this. Modern frameworks handle this automatically, but you need to know why. Second, gradient accumulation changes your effective batch size, but not your loss value, assuming you average rather than sum. If you switch from averaging to summing, your loss spikes and your learning rate schedule breaks. Always normalize by the number of accumulation steps. Third, auxiliary losses. In multitask systems, you often have a primary loss plus auxiliary losses for regularization or secondary tasks. The weighting of these losses is a hyperparameter that requires tuning. Too much auxiliary weight, and the primary task suffers. Too little, and you lose the regularization benefit. Uncertainty weighting, learning the loss weights, is an elegant approach that works well in practice. Wrap up. Loss functions are the optimization target. Everything your model learns, it learns because the loss function told it to. Senior engineers treat loss function design as a first-class architectural decision, not an afterthought. Know your loss functions. Know when to use each. Know how they interact with your data distribution, your class balance, and your training procedure. That's episode 70. If you got value from this, subscribe to Agentic AI World for daily interview prep. Tomorrow we go deep on optimizers, Atom, Adagrad, Lion, and the nuances that separate candidates who know from candidates who understand. See you then.